Hi biology students, this is Miss Miller again, and we're going to continue on talking about our unit in the chemistry of life. Today is section 2 where we're going to focus on chemical bonds. When you think about pretty much anything in nature, most of these things are going to be held together with chemical bonds. So it says compounds are held together by chemical bonds. We know that compounds are two or more different atoms that are chemically combined, and the way that they're combined are these bonds. Bonds are going to involve electrons around the nucleus. So in the nucleus, remember that's the middle spot, and then we can have 2 electrons in the first ring and then 8 in the next. But what we really want to focus on with bonds is the valence electrons. Valence electrons are the electrons in the outer shell and of an atom and that are responsible for the chemical properties of this atom. For example, lithium, we can see that there's 2 rings. Lithium has 1 valence electron, so we look at the outermost ring and it only has 1. Versus fluorine, when I look at the outermost ring, that one has 7. When we talk about bonds, today we're really going to focus on the 2 types, and that is the ionic and the covalent bonds. Some of these you'll probably remember from 9th grade physical science. The first type of bond that we're going to focus on is the ionic bond. An ionic bond is formed when 1 or more electrons are transferred from one atom to another. Up here we can see a great example of this, lithium and fluorine. Lithium is going to transfer this valence electron over to fluorine. Under normal circumstances, atoms are going to be electrically neutral because they have the same number of protons and electrons. So let's say we look at lithium. Lithium has 3 electrons. It also has 3 protons. However, it's going to transfer its electron over there, and it's going to lose an electron. So when that atom loses an electron, it ends up getting a positive charge because there's more protons than electrons. And remember, we call this the cation. Cation positive. Cats have paws. On the other hand, when I look at my fluorine, fluorine is going to be gaining an extra electron. Therefore, it has more electrons than protons, so it ends up with a negative charge. So this is our anion. Remember to keep track of that one, a negative ion. So when I look up here, this one, my lithium is my cation, and my fluorine then would be my anion. So these positively and negatively charged atoms then are known as ions. So ions could be positive or they could be negative. One important thing we want you guys to be able to do is identify what type of bond you have based on a chemical formula. So ionic bonds are always formed between a metal and a nonmetal. On this periodic table, we can clearly see that we have metals in blue and our nonmetals in yellows, and then these metalloids in green down the middle. Metals make up the majority of our periodic table. So that would be all the things in blue, except I do see one error on here, and I'm going to fix it actually. I'm going to make that hydrogen yellow because that guy, hydrogen, is actually a nonmetal. It's the only nonmetal to show up on the metal side. Nonmetals, on the other hand, are always on the right-hand side, but also we're going to see hydrogen there. What I want you to figure out is that anytime that we are taking something from the left-hand side and combining it with something on the right-hand side, or a metal to a nonmetal, we always have an ionic bond. Here we see a great example of an ionic bond occurring, and this is between a sodium, which is our metal in this case, I'm going to write M above that, and chlorine, which is our non-metal. So again, it's always with an ionic bond is between a metal and a nonmetal. So we have this sodium atom. We're going to look at its 1 valence electron, and it's going to give it away, and it's going to give it to our chlorine atom. Because sodium gets rid of an electron, it becomes the positively charged cation, versus the chlorine, as it gains the electron, becomes the negative anion. Remember, a negative ion is an anion. So this is a great example where we see a metal giving away its electron to a nonmetal, forming an ionic bond. The second type of bond that's really important for you guys to understand is the covalent bond. So in a covalent bond, electrons are shared by atoms instead of being transferred. So these guys are essentially like in a tug of war that no one can win. Electrons travel in the orbits of both atoms. And when the atoms share 2 electrons, the bond is called a single covalent bond. When it's a double or a triple, you can see that they're sharing more types of bonds. Here we see 2 hydrogen atoms. What these 2 hydrogen atoms are going to do is they are going to share these 2 electrons that we see in the middle, and these electrons can go around either one of those hydrogens. So they are sharing them instead of transferring them. When we talk about covalent bonds, you can quickly tell if you have a covalent bond based on what types of atoms are involved with this. Again, I'm going to go ahead and switch that hydrogen so that it should be yellow, remember, because that is also a nonmetal. But when we look at covalent bonds, it's always formed between 2 or more nonmetals. So covalent bonds are nonmetals only, or something on the far right side of the periodic table, or hydrogen. So don't forget about that hydrogen. So we could have hydrogen combining with carbon, and those two would make a covalent bond. Nonmetals want more electrons, so what happens is they want to share these guys, and they end up in this tug of war, and neither one can win that tug of war. That's why they end up sharing. So covalent bonds are different because we're dealing with the nonmetals on the right-hand side or hydrogen. So as I just mentioned, when we talk about covalent bonds, it's all about that attraction of the electrons. It's almost like it's a tug of war. What we're going to see is that elements do not all have the same ability to attract electrons. Some atoms have a stronger pull than others. Covalent bonds can share electrons, but that sharing is not always equal, and this is what we call a polar covalent bond. In this case up here, I see chlorine and hydrogen are trying to share these electrons. Chlorine has been able to pull on those electrons and brought them much, much closer to them. So we're going to see that we're going to get a polar covalent because the chlorine is stronger than the hydrogen. If you want to think about it like if we made the freshman class play tug of war against the senior class. The senior class is probably stronger and is going to be able to pull that rope closer to them versus the freshman class that's just trying to hang on to those electrons in general. Now that you guys have a basic understanding of what the 2 types of bonds are, we're going to talk about how we can draw these things, and what we're going to do is we're going to draw them as Lewis structures. So a Lewis dot structure shows the symbol and the valence electrons. So we see the symbol and the valence electrons when we go and we draw Lewis dot structures. These structures are important to know when we are talking about bonding. Up to this point, we've talked about these models. These are called Bohr models. But now we're going to work with just the valence electrons to do the Lewis dot structures. I personally like the Lewis dot structures a lot more. They're really, really easy to draw, and they're much simpler than those Bohr models. So when we go to write a Lewis structure, the first thing that we have to do is write out the element symbol. So here I have an example. My element that I'm working with is carbon, so I'm just going to put in the capital C. Remember, if there is more than one letter, let's say something like chlorine, it would be a capital letter first and then a lowercase letter second. Okay, so whatever you see on the periodic table is what you guys should write down. So first, we write down the symbol for that element. Next, we have to calculate how many valence electrons or electrons on the outermost ring that element has. You may be asking yourself, well, how the heck do I do that? Well, it's actually pretty easy. What we're going to do is we're going to look at the column the element is in, and this is from the periodic table. For columns 1 and 2, this is super, super simple. So with columns 1 and 2, what we're going to do is, if we know it's in column 1, it has 1 valence electron. If it's in column 2, it's going to have 2 valence electrons. But the rest of the periodic table is a little bit funky. So what we're going to do is in this class, we're really just going to focus then on columns 13 through 18 because these guys follow the rules. So with columns 13 through 18, what we're going to do is we have to calculate these a little bit differently. What we're going to do is we're going to drop the 1 in front of the column number to calculate the valence electrons. That's VE here. So carbon, for example, is in column 14. So I'm going to drop that 1, and I'm going to find out that it has 4 valence electrons. Just like oxygen, it's in column 16. Therefore, it has 6 valence electrons. So all I'm doing is dropping that 1 in front, and you're left with how many it has. To finish this Lewis structure, it's very simple. Now that we know how many valence electrons the atom has, we're simply going to draw each one as a dot around our symbol. You can add 1 dot to each side of the symbol before you start to pair them. There's a maximum of 2 dots per side, so those are important things. So we can have 1 dot per side before we start to pair them. And we also have a maximum of 2 dots per side. So we can see our example of carbon here. Carbon's in group 14. It has 4 valence electrons, so we put 1 on each side. If we go back to that example I just talked about on the previous slide with oxygen, you guys remember that oxygen is in group 16, so it has 6 valence electrons. So I'm going to go 1, 2, 3, 4. Now, because I have 1 on each side, I can start to pair them up. So I'm going to go 1, 2. And when I count that, I should see I have 1, 2, 3, 4, 5, 6. So that would be our proper Lewis structure for oxygen. The last thing that we want you guys to be able to do is once you're able to draw a Lewis structure for a single atom, we also want you guys to be able to do this for the bonds. So for our ionic bonds, we have electrons that are transferred from the metal to the nonmetal. So what do we do with these things? We represent these with arrows. So for example, my calcium's in group 2, therefore it gets its 2 dots. Chlorine, each one, is in group 17, so it has 7 valence electrons. What we want to do is metals want to give their electrons away, the nonmetals want to gain more. And remember, we're looking for that rule of 8. So what calcium is going to do is going to give 1 over to this chlorine. Then this chlorine is happy because it has 8. And it's going to give its other one over to this chlorine, and it's going to be happy. Notice that the arrow goes from the metal to the nonmetal. Okay, from the metal to the nonmetal. And the arrow shows that it's transferring. Covalent bonds are a little bit different. These guys are going to be represented by a solid line. And what we're going to see with these, because it's a solid line, it's showing that they're shared. And each line represents 2 electrons. So here I have my nitrogen in the middle, and then I have my oxygen and my chlorine. What we see is my oxygen as 2, 3, 4, 5, 6. And remember, this line counts as 2, so it has 8 around it. We consider that one to be happy. Then what we're going to do is we're going to look over at our chlorine. We see 1, 2, 3, 4, 5, 6, 7, 8. It's also happy. The only thing that is missing on our nitrogen is it should actually have 2 more little dots around it, and then it would be happy as well. So covalent bonds use lines. Ionic bonds use arrows. If you have any questions, please let us know. Otherwise, have a great day.